All right. Hello, everyone. Good morning. This is Unit 2, Office Hours. Unit 2. In case you're here looking for Unit 1, this is Unit 2. I'm Russ. My name is Russ. I'm back again here today for Don. Don is occupied today. That's why I'm here for Don. This is for Unit 2. So double check that you are in the right place. Let's see here. Let's double check my calendar and make sure that I know what I'm talking about. So, yep, Unit 2, office hours right now. What questions could I answer for you today? Don told me he was looking at the ML project yesterday. Told me I might want to go over again question 5. Yep, Capitan, this is office hours for Unit 2. Office hours for Unit 1 will be later today. Hello, Redot. I'm fine. It's a busy week. So far, so good. Although it's only Wednesday, I kind of wish it was like Thursday or Friday, but, we'll get there. I hope you're doing well yourself. Let's see here. Let's tidy up my notebook a bit. Oops, I just deleted the greater cell, didn't I? Looks like I did. That's easy enough to fix. Undo. Undo it again. Undo it. There we go. Right, so let's delete these things here. So on Monday, I talked about this question for this business model, right? We wanted to combine our two features together. And so defined, put the features together with a feature union, and then we put these features into a pipeline of some form. Added on some polynomial features, tried a random forest classifier, a bit of grid search here. So, hello, Renato. This fifth question right here, it's a bit different in some sense. So, said here, surveys So the idea here is there's multiple surveys that go on. If we look at our data, so data.head, remember these are nursing homes, providers. We have different kind of information about nursing homes. There's two kinds of, there's two surveys that we have information about here. We have a cycle 1 total score. We have a cycle 1 survey date, a cycle 2 survey date. I always thought we had this question slightly in reverse. Because you want to build a model that combines the business features of each facility with its cycle 1 survey results, as well as the time between cycle 1 and cycle 2 surveys to predict the cycle 2 total score. I always thought this should be reversed. We seem to, but so we want to take the business features and the cycle 1 survey results and the time between the cycle 1 and cycle 2 survey dates. And we want to predict this cycle 2 total score. All right, so we have like one results of surveys, and we want to predict results of another survey together using the business features of the facilities and, as I said, the time between these two survey dates. So we need to build a transformer of some type which will give us the time between these survey results, these survey dates. We have provided a transformer which is mostly filled in. We just have to fill in the transform method. So the idea here, as it says, is that we want to build a transformer. So this will take a data frame. Well, we have to deal with like what you did earlier, that the input could actually be a list of dictionaries. If we get a list of dictionaries, we want to translate that list of dictionaries into a data frame. But that's easy enough to do. We check if not is instance of X, and is X a data frame? Well, then we translate it into a data frame. Right, again, our training data here is in the form of a data frame. But remember, new data we're getting from the grader will come in the form of a list of dictionaries. And so we just want to handle that possibility, that if our data is this list of dictionaries, so if it's not a data frame, I want to translate it into a data frame, right? If it's not a data frame, it's going to be this list of dictionaries. So I'll first translate this into a data frame. Why am I doing this? Well, because I want to refer to column names of this data frame. So this T1 column, T2 column, these are going to be strings, i.e. names of columns in this data frame. Now, what are these data types of, data.dtypes? These, this survey date, the cycle 1 survey date and the cycle 2 survey date are objects. These are basically strings. I could translate these strings into pandas date time objects. Why do I want to translate them into date time objects? Well, because I could do date time arithmetic on date time objects. Right? I could say this day, minus this other day. So, for example, PD to date time. If I look at data, cycle 1 survey date. All right, these are date time objects now. If I were to convert, this other column, so PD to date time data cycle 2 survey date, I could do arithmetic. I could say I want to subtract one series of date times from another, and I get a number of days. Right, this is the benefit of using date time objects. I could do arithmetic on these date time objects. And by I mean, of course, pandas can do this for me. I can get the values out right here in terms of, this now comes out in terms of a number of nanoseconds. It's still date times. What I might do is then I might convert these to floats. Right, so then I have numbers that I could use in a machine learning algorithm. Because, of course, that's basically what we need. We need numbers that we could fit into a machine learning algorithm. So what I want to do is, after I've converted my input into a data frame if necessary, I will convert, I'll say to date time. I will take my T2 column, minus PD dot to date time x self dot T1 column. I will get the values. Let me put some more room in here. I will convert these to floats. And then one last thing I want, this was coming out as a one-dimensional NumPy array. Remember, I want to convert this to a two-dimensional object. Because I want to use this as part of my feature matrix in my inputs. So I want to convert this output into a two-dimensional NumPy array. So I want to reshape this into a column. I could try this out. Right, so once again, convert this column into dates and times, convert this column into dates and times, take the difference, convert these to just take the values. This will be a series, take the values, convert them to floats, reshape this into a column vector. Now I could try this out. Time feature, time delta transformer. I could try this out. I could say time feature transform on data and give me the first 10 rows. All right, positive, negative, well, it doesn't kind of matter as long as I'm consistent right here. All right, this gives me my two-dimensional NumPy array that I want to use in a feature union. So I want to take my business features that I had before, which we had from the previous problem, take my business features, make a feature union together with these differences in times, and add in features for this cycle 1 survey. Well, this is, we could use this column select transformer that we defined way back in problem 1. Or problem 2. Where is this defined? Problem 2. We had this column select transformer which we could use to grab these columns for this cycle 1 survey information. So I could say, all right, I want my column select transformer on my cycle 1 columns, this list of columns up above here. Now I put together all of my features. And well, this is partly done for us right here. Right? We have a feature union which takes our business features, our cycle 1 features, and our time feature, puts them all together into one big feature matrix. If I just define this pipeline here for the moment, no estimator, my pipeline is a transformer. Survey model dot fit transform on my data and say I take the first, 3 rows, then this is my new feature matrix that we get by putting together our business features, our cycle 1 features, and our time feature. Here's our new feature matrix right here. Now we say, all right, we want to add in our estimator here. Well, there's an obvious suggestion. We could try a random forest regressor, right? We're trying to predict the score, the cycle 2 score. This is no longer a classification problem. This is a regression problem. We're trying to predict this score. So I might say, all right, well, I take my features. I'm going to do a random forest regressor. So random forest regressor. There's many things I could tune here. I could say, well, the number of estimators, let's take to be arbitrarily 100. If I want some repeatability, I will set the random state to be, 17, my favorite prime number, because it's the best prime number of them all. I could do survey model fit. I'm looking for my data. And previously, way up top right here, we had saved this cycle 2 score. This is the target now. This is what we're trying to predict. Oops, we have this fit right here. Let's use that. So survey model.fit data cycle 2 score, say as type int. We fit our model. This could take a bit of time to fit. Right, we have a larger feature matrix. This is a regression problem. We have a random forest regressor. There's a number of decision trees to fit. If you're using a random forest regressor, you don't have to scale your features. That's a good question, though. It's a good question, but using a random forest regressor, we don't have to scale our features. If I was using something like linear regression or ridge regression, I probably do want to scale my features. But a random forest regressor, remember, a random forest regressor is a collection of decision trees. Each decision tree is just doing this procedure, right? Ask a question about your data. Is this feature less than or equal to this number or greater than or equal to this number? So if you're using a decision tree or a random forest, you don't have to scale your data before passing it to that decision tree regressor or random forest regressor. But if you were doing linear regression or ridge regression, lasso regression, then you would want to scale. So yeah, trees don't really require scaling. Because, remember, they're not fitting coefficients to the model. They're asking questions about the data. We fit our model. I could look at, so survey model score, data, and my cycle 2 scores here. Let's copy, paste here. All right, remember, what is score mean right here? What is this number that I'm getting out from the score method of the survey model? We were having an error that was asking for a float conversion as you did. Why is that? The float conversion here. Well, basically because these values come out as a different data type. They come out as a time delta object or a dates time object. And so we just want to make sure that the machine learning algorithm will treat them as numbers. So, well, let's convert these to floating point numbers. So I said this difference right here will come out as this is, so like I was doing here, if I remove this as float, the data type is a so-called time delta 64 data type. And if you try to combine this with numbers, for example, well, this could give us a data type error. So instead of treating these as time delta 64 data types, well, let's convert them to floats. So as type float. And then these are floating point numbers. So back to my question, we fit our model. If I look at the score function of the model, I get this number out here. What is this number? What is this telling me? What does the score method tell me? All right, this is a regression problem I'm doing. Yeah, this is an R-squared score. R-squared score is pretty good. I could try this in the grader. My score on the grader is pretty low. Why might that be the case? I mean, there might be several reasons why this is the case. And what may I do about trying to raise this score? The score from the grader. Remember, the score from the grader is basically comparing the model we built in terms of the R-squared score versus the R-squared score of the model solution. It could be overfitting. It could be as well that my features aren't very rich enough. What I could do, for example, is we could add in some polynomial features into our pipeline. Like after the feature union, I might say, well, let's engineer some more features. Now this polynomial force requires. Oh, sorry. Polynomial features. I will refit my model. This could take a lot longer if I have these polynomial features. Because I basically squared more or less the number of features that I had before. Yeah, I could be overfitting. I might need to adjust things on my random forest regressor. I put no conditions on things like the maximum depth, or the min samples leaf, or the min samples split. Right? I might need to maybe do some kind of grid search to find good values for these parameters. I might, but of course grid search might take a while. I don't want to sit here, for 10 minutes while we're doing a grid search, but, it could be something that you guys could try out. Because, even without a grid search, well, the random forest regressor is starting to take a long time because I have a much larger number of features. Polynomial features, as I said, basically, squares the number of features you have because of the degree 2. Meaning we were doing a linear regression, and though R squared was high, fitness could be better done by a polynomial regression. Yeah, that's kind of the idea. On the other hand, I could end up overfitting even more. Probably the problem is likely that I want to limit the random forest regressor in some ways, right? I've let the maximum depth be as large as we want it to be. I'm probably overfitting. So I probably need to impose some limits on my random forest regressor so that I will then do what? I will decrease the variance of my model. I'm probably fitting some of the noise that's present in my data. So I'm overfitting, and my model isn't generalizing very well. If I'm using polynomial features as well, I might consider reducing the dimensionality after polynomial features, right? I generate new polynomial features, but then I might consider doing something like the truncated SVD to reduce the number of features down to something that's a bit more reasonable. And truncated SVD is also a way that we could consider removing the possibility of some overfitting, right? Remember truncated SVD. I don't know if you talked about this a lot, but we're looking to map into a new feature space, and we're keeping most of the variability. But by removing some of these features with the smaller variability, well, we're removing some of the noise that's present in our data. So truncated SVD is one way of possibly removing some of the variance so that our model might fit a bit better, might generalize a bit better. And I could impose some limits on my random forest regressor in an effort to reduce the variance, reduce the overfitting. Indeed, I might want to just abort this fit method because it's taking so long. And, impose these limits now because, well, we're probably going to have to do that anyway. So let me actually interrupt the kernel here. So, for example, I might, after polynomial features, let's do a dimensionality reduction step. Do truncated SVD, the number of components. Let's, again, somewhat arbitrarily, I'll take to be 30. Let's take min samples leaf, again, arbitrarily to be 20. Oops, truncated, I missed a comma. So this should bring my, fit step back down to something which is a bit more reasonable in time. I mean, there's some time needed to do the truncated SVD, but I could do things like grid search, but that's kind of dull to sit here watching, that grid search happen. That's the kind of thing that you guys should probably try out. You could do grid search on, say, changing the min samples leaf, changing the max depth. Maybe try some different number of components in the truncated SVD. There are lots of things that you could try out. Our score, our R-squared score, is much smaller. But on the other hand, our model generalizes well. Right? We were probably massively overfitting to our training data. And this is because, we were allowing the random forest to grow as much as possible. And, basically to the point where it was probably able to, perfectly reproduce the training data. I mean, still not perfectly reproduce. You could see the R-squared score wasn't 1. But it was very high. And so we were likely massively overfitting to the training data. And remember, right, one of the goals in machine learning, of course, is we want a model which will generalize well to new data. So is there any question on what I've done right here? Right, we take our features, we've engineered more features, but then the dimensionality reduction should serve to remove some of the noise. And then we pass this data to the random forest regressor, and again, I want to impose some limits on the decision trees so that as to not overfit to the data. I could change things like the min samples leaf. Right, raising min samples leaf will, in general, could tend to raise the bias, but will also tend to lower the variance. right? And the thing to keep in mind, and we're doing machine learning, we're always kind of looking for that sweet spot. I want to find the signal that's present in our data between the independent variables and the target. I want to find that signal without capturing much of the noise. So it's that sweet spot we're always looking for. We can't necessarily always find it, or or we might not find kind of the exactly right parameters, but we're looking for something which is close to that if we can. So any questions on anything I've done here? Right, I'm sure Don's been saying this to you as well, right? You basically have to get your hands dirty. You have to try these things out and see what kind of effect you have. It's very useful to read the documentation of all of these tools in scikit-learn, right? I look at a random forest regressor. What options do I have in a random forest regressor? These are all sorts of things that I could possibly change: min sample split, min samples leaf, min weight fraction leaf, max depth, max leaf nodes. I could even change the number of regressors, the number of estimators. The random state I can use for repeatability across different, trials of fit. Remember, a random forest regressor has a feature importances attribute, although this becomes a little bit difficult to interpret if I'm doing something like truncated SVD. Because of course, truncated SVD, I have new features which have some relation to the old features, but it becomes harder to figure out, right? Especially as well when here I'm doing a polynomial feature, so I'm raising the number of features and then I'm lowering the number of features, and then the feature importances becomes really more difficult to kind of trace back to the original features I have as inputs into my pipeline here. The adding features and removing features, adding features and removing features, makes things difficult to unwind these original feature importances back to the original features I started with. Truncated SVD. Right, and we're not expecting you to be experts straight off the bat, but I also think reading the documentation right here, when I was learning about the tools in scikit-learn and doing machine learning, right, reading a documentation helped me learn even more about machine learning, right? What's going on behind the scenes? You know, there's all sorts of links right here. Oh, read more in the user guide. Okay. You know, there's examples down below here, right? Manifold learning, handwritten digits, hashing feature transformation. You know, examples that I could read. Read more in the documentation. You know, read more in the user guide. Okay, I'll spend some time reading the user guide. You know, what is this? So it implements a variant of singular value decomposition. All right, if I didn't know what singular value decomposition is, I might go read more about it. It only computes the k largest singular values. K is a user specified parameter, etc. All right, so really lots of good stuff to read about in all this documentation. It's highly worthwhile spending some time, you know, reading some of this documentation, especially, oh, you know, I've learned about something new. Oh, here's a new regressor that I've just learned about. Okay, what options does this have? What are things that I could tune? How does this work? You know, what attributes is it computing? What is it? You know, so on. Thinking about how these things you could change, how they might affect your bias variance trade-off. So yeah, what other questions could I try and answer for you guys today? You know, I don't generally come into these office hours with any sort of agenda of my own. I'm looking for questions from the students. So what questions do you all have? Remember, of course, that if you go to the control panel here, you could find your grades on your mini projects, right? Grades. We always record the highest grade. So, you know, right, I have this score of 1.174 on this survey model. I could go back and I could try something else. If I get a lower score on the grader, well, it doesn't matter. We keep the highest grade. Yeah, you know, yeah, like I say, yeah, you got to get your hands on the keyboard and try things out. That's the only way that I really learn how to write this code correctly, how to use the tools correctly. Can you talk about multi-class classification problems? Are those ones that have multiple labels? In my mind, well, the multi-class classification problems are ones where you have more than two possible labels. So the ones that have multiple labels, I would tend to refer to those as a multi-label classification problem. So let's make a new board. So multi-class multi-class might be, well, I have more than two possible labels. I have labels A, B, and C, or A, B, C, and D. Right? These are, say, possible values of my target label. I want to predict which of these four categories an observation belongs to. There's multi-label. I might have my label, say, is more than one thing, right? I might have I have this label 0, 1, and I might have a label 0, 2, and I might have a label 1, 3, or whatever, right? The labels have more than one component to them. Now, multi-label, you could either treat each portion of the label independently and just do a classifier for each portion of the label. One way that I might also consider doing this as well, you can actually kind of map this back to a single label multi-class problem. Right, like, 0, 1 is some label alpha, and this is some label beta, and this is some label gamma. Right, just kind of treat every possible pair as its own unique label. Right, so I might think, well, map to a multi-class problem. Right, even though there may be more than one label, well, just kind of map the pair to one unique label. Whether this is a good idea or not could be up for debate. Alternatively, we could just say, well, treat each portion as its own separate classification problem. Just kind of ignore this part. All right, here I have two classes, 0 and 1. Build a classifier for two labels, 0 and 1. Then I will ignore this other part. Here I have three classes. Build a classifier for those three classes. And then just kind of, take, these two classifiers and build the pair of labels. Multi-class problems. Well, have you talked about how you deal with multi-classes? The idea is relatively straightforward. Now, this is something that scikit-learn helps to do this automatically for us, right? If we have more than two labels, we kind of don't have to treat those differently using scikit-learn. So what you do in general is you treat this as a collection of, of binary classifiers. like we think about grouping our data, I have the class A, and I will have the class that I will call not A. Right? I group everything together here as one class and treat this as another class, and we build a classifier, a binary classifier for A versus not A. We could build another binary classifier for, B versus not B. And C versus not C, and so on. And then the idea, we'd say we'd have 4 classifiers in this case, one for each of our original class. We have these 4 binary classifiers, and we want to bootstrap our way back up to a classifier for the 4 original classes. And one way that we could do this is, well, remember that these classifiers are actually giving us probabilities. Something like logistic regression or a decision tree classifier or a random forest classifier right there. They're actually predicting probabilities. The probability of belonging to one class or another. And the idea is, well, we could use those probabilities from these 4 classifiers to bootstrap our way back to a classifier for the original 4 classes. In a kind of adding normalization kind of procedure. And that's what scikit-learn actually does for us. Again, if I look at something like logistic regression, which is a classifier, of course, despite having the word regression, this is a classifier. We have this multi-class option, which is auto in this case. I come down here to the multi-class option. We have auto, OVR, and multinomial. They say if the option is OVR, a binary problem is fit for each label. Which is what I talked about, right? Change it into a set of binary classifiers and then bootstrap our way back to the original problem. For multinomial, I said the loss is minimized as a multinomial loss. I don't want to get into these details. They're a bit more complicated, right? And the idea is, they said this was changed from OVR to auto, and auto, scikit-learn is supposed to make some kind of informed decision as to go for OVR or multinomial. Right, but basically it's more or less going to usually default to OVR, which is this set of binary classifiers, and then we bootstrap our way back to the original problem. So hopefully that makes sense. I see that I'm out of time for today. I have another group of students to go teach in half an hour, so I need to go prepare for that. Dawn will be back tomorrow. Regular services will be resumed next week. So I will wish you a pleasant afternoon, and as I said, Don will be back on with you guys tomorrow.